Alright, welcome to our fourth video of our fifth unit of AP Chemistry. Again, this is our thermodynamics unit, and this video will talk about the enthalpies of reactions, basically using enthalpy. So, the enthalpy change that accompanies a chemical reaction is called, rather unoriginally, the enthalpy of reaction. And we denote it by, again, remember we don't really calculate enthalpy, so we find our change of enthalpy of a reaction. Now, that is the abbreviation for reaction. Please know that. It's kind of useful. Rxn. Whenever we provide such a value, we must also supply the reaction it is associated with. That heavily matters, as you will very shortly see. In general, a reaction proceeds from reactants to products, and so any energy change occurs due to this process of reactants converting to products. So our enthalpy of reaction, therefore, can be determined by combining the enthalpy, wow, that's not spelled well, the enthalpy of the products and subtracting the enthalpy of the reactants. Basically, our reaction is our products minus our reactants. Now, you will notice there's no delta H here. That is because we are actually adding up a special type of enthalpy. We will see that shortly. All you really need to remember right now is delta H refers to products minus reactants. Please keep that in your mind. So, there are three important pieces of information about enthalpy that we have to understand before I can really do much else with enthalpy. So, let's talk about it. First off, enthalpy is what we call extensive. That means that enthalpy change is dependent on the amount of the substance involved, meaning the more heat is applied, the more energy is transferred, or the bigger the amount of substance, whatever, the larger the enthalpy change. Now you're thinking, well, duh, Mr. Booth. Well, let me give you something that's not extensive. Density. I don't care how big of a sample of wood you have, it's going to be the same density as a smaller sample of that same type of wood. You're always going to have the same type. Yes, it will take more heat to heat up the whole thing, but it still has the same density. So a smaller substance thus will have a smaller enthalpy change than a larger substance if they both experience the same temperature change. So if you got a small object and a large object, and you both raise them by 5 degrees Celsius, you're going to need a lot less heat to heat up the small one, a lot less energy. Wow, that gets confusing. To heat up the small one than you will the large one. Think about trying to get a cup of water to boil versus a pot of water to boil. All right, secondly, the reverse enthalpy is negative. This is why our equation matters. Energy transferred into a system is the same quantity as that transferred out of the system, but the enthalpy change of the reverse is the same in quantity, just negative in sign. So back to that whole, hand with ice. Basically, what we're saying is that there's the same energy that's being transferred from your hand into the ice. From the hand's perspective, let's pretend, that's 10 joules. From the hand's perspective, we're losing 10 joules. From the ice's perspective, we're gaining 10 joules. That means from the hand's perspective, we are exothermic with 10 joules. And from the ice's perspective, we are endothermic with 10 joules. Same number, just negative, because it really depends on what perspective you're looking at. Thirdly, enthalpy depends on states. Different states have different amounts of average kinetic energy as discussed before. Enthalpy change depends on what states the reactions/products are in. Basically, you got solid, liquid, gas. There are more, we don't care. Enthalpy increases going this way. Because think about it, you need more energy to keep something as a gas than you do to keep it as a liquid, than you do to keep it as a solid. So enthalpy will increase as you change states. Alright, so let's do an actual example. And this did not come out well. Sorry guys, hopefully you can read it. So the complete combustion of ethanol with a formula weight of that, please keep in mind that represents molar mass, hopefully you remember, proceeds as follows. ethanol, you burn in oxygen, you get carbon dioxide and water. Yay, typical combustion reaction. That is quite exothermic of negative 555 kilojoules. What is the enthalpy change for combustion of 15.0 grams of ethanol? All right, so we're saying this is the energy that happens when this reaction occurs. We're saying, but what if we have 15 grams of ethanol? Well, my AP students have been complaining for the last month that we don't have enough stoichiometry problems. So if you're a general student or honor student reading this, yes, I seriously said that. And if you're an AP student, you finally have stoichiometry again. You're welcome. Because this reaction is when 1 mole of that reacts. But notice we have 15 grams. So that means we have to get grams, 2 moles, and then moles to kilojoules. Yeah, that's new. All right, so let me show you how to do it. You got 15.0 grams of ethanol. Okay, we're going to 1 mole of ethanol. And unfortunately, they told us the formula weight is 46.0 grams. Why they told you is because it looks scary and they don't want you to be scared. I really don't know, actually. Okay, but now that we're in 1 mole, this reaction happens when 1 mole of ethanol combusts. So that says that we are going to produce 555 kilojoules for every 1 mole of ethanol. Now, hold on. Wait, Mr. Booth, isn't that a negative up there? And yes, it is. While that tells us how many joules are released, that also tells us our direction. So don't forget the negative. If they were asking you for how many joules are released, you can just keep it positive. But since they're asking us for the change, that means they need to know whether things are going to be increasing or decreasing, so we have to keep the sign. All right, but you take 15 divided by 46 times negative 5 of that, you get negative 181 kilojoules. Now again, they did ask us for the change. We have to keep the negative. If they had said how many kilojoules are released, we could have left it as positive because we could have said 181 kilojoules are released. They didn't, so we have to keep it. But that's your answer. Now, keep in mind that if we were dealing with oxygen, this down here would have been 3 moles of oxygen. Or if we were doing carbon dioxide, this would have been 2 moles of carbon dioxide. This represents the coefficient here because this reaction happens according to these ratios. So, just reminding you. There you go, though. Those are enthalpies of reaction. We'll use more, but this is kind of the starting place of enthalpy. This is actually probably the most common one in real life because you can literally say, here's my reaction. How much fire am I going to get when I burn this much stuff? That's kind of what you're asking. So, thanks for watching as always. Have a great day.